Hello and welcome to EngPhys 3004, lectures 12 and 13. First off, mechanisms of heat transfer. This is where we start the second half of the course, looking at how heat moves around. First mechanism is conduction. Conduction is heat flowing through an object if the pieces of the object aren't moving around relative to each other, besides thermal oscillations. So in conduction, the rate of heat flow is given by the thermal conductivity, K, multiplied by the cross-sectional area to the direction of heat flow, and then multiplied by the temperature gradient, the rate of change of temperature in the direction of the heat flow. So the negative sign tells you that heat is going to flow from higher temperatures towards lower temperatures. So in negative, the direction of the temperature gradient. Here we're looking at dt by dx. This would be if temperature is only changing in the x direction, or if we're only looking at the rate of heat flow in the x direction. The second mechanism of heat flow is convection. Convection incorporates fluid motion into conduction. So convection is heat flowing from one object to an object next to it. So from one molecule to the molecule next, or one atom to the atom next to it. And then the atoms are able to move, maybe because there's some external fluid motion, or perhaps fluid motion because of the difference in heat in each section of the fluid itself. So in that case, where the fluid motion is caused by differences in density from different temperatures, we have what's called natural convection. If the fluid motion is there regardless of the heat transfer, then that's forced convection. Either way, the rate of heat flow in convection is proportional to a convection coefficient, H. This has to do with how the fluid is moving, properties of the fluid that we're going to look into in detail in chapter 19, but for now it's just a constant, and will have to be given in the question, multiplied by the cross-sectional area. And so really cross-sectional area for convection, this is looking at the heat flow from some solid surface, so the surface that is in contact with the fluid, and then multiplied by another temperature difference here. So this is temperature of the surface minus the free stream temperature of the fluid, so temperature of the fluid far away from the surface. The third mechanism is radiation. And here we have the Blackbody radiation formula. So this is the Stefan-Boltzmann law for a blackbody anyway. The rate of heat emission is the Stefan-Boltzmann constant multiplied by the surface area multiplied by the temperature to the power of 4. And for this, you have to use the absolute temperature in kelvins. Now we're going to spend a section on each of these in turn, looking in a little bit more detail in chapter 16. Even though chapter 16 is still broadly an overview chapter, we're going to look in more detail at each of these in turn, and then discuss simultaneous mechanisms of heat transfer to close the chapter out. All right, conduction in detail. Rate of heat flow through conduction is the thermal conductivity material parameter multiplied by the cross-sectional area multiplied by the temperature gradient. So this is looking at the rate of heat flow through some cross-sectional area, or the rate of heat flux through that surface. Now, if the surface area is a constant, as in a setup like this, where you've got insulation here, insulation here, insulation here, the heat can't be flowing through those insulation areas. So all the heat must be going this way. We've got constant cross-sectional area. If we're looking at steady state, then the temperature isn't changing at any point, so the heat isn't building up at any point. So all the heat that flows through this first cross-sectional area has to flow through the same, has to be the same all the way along, because it also has to flow through these other cross-sectional areas and flow out the material. Same heat flow through all the different cross sections. And that means that the heat flow is a constant, Q dot is a constant everywhere in this object, cross-sectional area is a constant, and the thermal conductivity is a constant of the material. And that means that the temperature gradient also has to be a constant. So if that's a constant, it means we have a linear temperature distribution across the material, and that's how we get this straight line for temperature in this setup. So what you could do to measure the thermal conductivity is make a setup like this, have some way to measure the temperature on the inside, maybe with a thermocouple, measure the temperature on the outside with a different thermocouple, and measure how much power this heater is consuming to know the rate of heat flow, because all the power consumed goes into heat and must be giving you the rate of heat flow too. So that's how you could figure out the thermal conductivity of this material. Let's look at thermal conductivities for some different materials now. We see diamond up at the top here, 2300 watts per meter Kelvin. By the way, you can check for yourself that the degree Celsius or equivalent Kelvin unit has to be in the denominator of thermal conductivity by comparing to this formula or even Fourier's law directly to see what the units of thermal conductivity have to be. So we have diamond at the top, and then 5 orders of magnitude down, we've got air and some rigid foam here. So general rule is that heavy gases have less thermal conductivity than light gases, than heavy liquids, than light liquids, than amorphous electrically insulating solids, so like a glass, then metal alloys, then pure metals, and finally the non-metallic crystals being up at the top. Here's a chart of this. Non-metallic crystals most conductive generally, and then gases least conductive. Notice that metal alloys, like bronze, end up being less conductive than pure metals. So if you take copper, tin is going to be somewhere around here, similar to where iron is, and yet copper by itself, iron by itself, or tin by themselves, have higher thermal conductivities than if you push them together into bronze. That's kind of interesting. So alloys of the same two metals will have a lower thermal conductivity. To get an idea for some of the interesting things in this table, like why it is that crystals are up at the top here, and why it is that pure metals end up having better thermal conductivity than alloys of those metals, we can look at the mechanisms of heat transfer. So in a gas or a liquid, it's via molecular collision and molecular diffusion, whereas in a solid, there's 2 mechanisms of heat transfer. There's electron flow and there's lattice vibrations. So in a metal where you have electron flow happening, you know it's going to be a pretty decent heat conductor. In an insulator, if something's a bad heat conductor, then it means that there must not be very good flow of electrons or very efficient lattice vibrations. So there must not be a very good lattice to transmit information, transmit heat from one section to the next. And this explains why all good electrical conductors are good thermal conductors. All bad thermal conductors are bad electrical conductors. But some really great electrical insulators, like diamond, are also really great thermal conductors, because even though electron motion is inhibited in those, mostly because there aren't any electrons that can conduct electricity, the thermal oscillations, the lattice vibrations, are so efficient in those materials that they end up being fantastic thermal conductors. Thermal diffusivity is another property. It represents how fast heat diffuses through the material. So this is a ratio of the conductivity and the heat capacity. This is something that's a fair bit more important in transient heat conduction rather than the steady state heat conduction that we were looking at up in this example here. All right, next up is convection. There's 2 different types: forced convection, where the fluid flow is not due to the temperature flow, and natural convection, where the fluid flow is due to buoyant effects from the temperature flow itself. So as the hot egg transmits energy to the air around it, it's going to cause that air to heat up and then become less dense, and that's going to cause it to move. So you have more fluid flow than just conduction. And thus, even if you don't have a fan on the object, the proper model for something like air around a hot object is natural convection rather than conduction through the air for most purposes. Convective heat is pretty complicated, and that's mainly because we can't easily figure out what H is until we have the material from chapter 19. Again, that's going to involve some details of conductivities of the fluid, as well as information about how the fluid is flowing. So chapter 19 is all about forced convection. There's another chapter on natural convection, which we unfortunately don't have time for in this course, but it's still in the textbook. If you want to check that out, definitely a good read. Love to plug the textbook when we can, so really thankful for all of the great images that we have from them. Either way, for this chapter, we just need to know that convection is going to, all of that fluid information we can combine into the convective heat transfer coefficient H, and then once somebody has done that for us, it's pretty easy to calculate the rate of heat flow with convection. All it is H multiplied by the surface area that we're convecting heat from, multiplied by the difference in the temperature of the surface and the temperature of the fluid. So let's look at some orders of magnitude. H for free convection of gases, quite small. Free convection of liquids can be higher, but not necessarily. Depends on the liquid itself, although it can be a fair bit higher. Forced convection of gases, factor of 10 higher than free convection. Again, this depends a lot on the fluid flow too. Forced convection of liquids, fair bit higher than the free convection of them. And then boiling and condensation can be quite high. We'll look into this again a fair bit later in subsequent chapters. For now, why boiling and condensation can be higher than the rest of the convection coefficients is because at the surface, when we don't have a phase change going on, then we transfer heat from the egg out, and then as soon as the little bit of fluid outside gets to the same temperature, gets that heat, then there's no more drive for the temperature flow to happen. It has to kind of move away before any more heat can flow. But in a boiling reaction, increases in energy don't necessarily increase the temperature if they're going into making a phase change happen. The final process in detail is radiation, and now technically this is a volumetric phenomenon. Every molecule of an object, every atom of an object is radiating energy away just from its being composed of charged particles like electrons and positively charged nuclei, oscillating from their thermal energy. Moving charges radiate away energy, and so electromagnetic radiation should be showing up just from the temperature of an object. And this is given for a complete object, for a real solid, the internally radiated energy is recaptured. So for most practical purposes, we consider it a surface phenomenon, even though technically speaking, it's a volumetric phenomenon. Anyway, the Stefan-Boltzmann law is the main source of information for this. So this tells you for a black body, the total rate of emitted energy is equal to sigma, the Stefan-Boltzmann constant, multiplied by the surface area of the body, multiplied by its absolute temperature to the power of 4. Now, this has a spectral distribution that is important for a lot of processes. You want to know what wavelength the body is emitting at. And this is also the source of where you see things talking about color temperature. So when you set your monitor to a different color temperature, it's telling you where the most energy would be at various temperatures. So as this formula just tells you that increasing the temperature means more energy, but in addition to that, more energy being output ends up being having its peak at higher wavelengths, and that's where the color temperature part of it comes from. For us, though, we just need the total energy that's emitted, so the total rate of energy emission, and that's just the Stefan-Boltzmann law. Again, this is for a black body. For any real object, we also have to multiply by the emissivity, which is the symbol epsilon, and that's going to be between 0 and 1. Kirchhoff's law of radiation says that the emissivity and the absorptivity of a given surface at a given temperature and wavelength are the same. So any object that's a really good emitter is also a really good absorber. And that's why we're talking about black bodies being the ideal perfect emitters of thermal energy, because they're also perfect absorbers, and that's why they appear black. So if you look at vantablack or some other kind of amazing modern material, it actually is kind of impressive to look at. It looks like there's some sort of an optical trick where there's a hole there, when really it's a surface that is absorbing nearly all of the incoming light. So here we have a table of emissivities at 300 K for some different objects. You can see that shiny metals are going to be having very low emissivities. That's because they're quite reflective, whereas things that are not reflective, like black paint, are going to have very high emissivities. Okay, when an object is completely surrounded by another object, then what we're most concerned with is probably the net thermal radiation, and this is the amount that's emitted away minus the amount that's absorbed back in. If the other surrounding object is all at one temperature and much larger, we don't have to consider its surface area, just the surface area of the body here is the limiting factor. So our net radiative heat transfer formula that we're going to use most of the time is actually this one, and this is appropriate for, say, a person sitting in a room where all the walls are at the same temperature. Doing some manipulations here, you can take some differences of squares in the radiative heat transfer terms and separate out a raw temperature difference between the surface and the surroundings, which is useful if you're going to combine that with convection, because that's the same kind of formula that we have in convection, assuming that the temperature of the surroundings is the same as the free stream temperature of the fluid. Then what you can do is define, similar to convection, an effective radiative heat transfer coefficient by lumping all of these terms, emissivity, Stefan-Boltzmann constant, and these factors of absolute temperature into one parameter called the radiative heat transfer coefficient. And then, in fact, you can even add that to convection and form the combined heat transfer coefficient. Finally, simultaneous heat transfer mechanisms. You can't have all three mechanisms at once. In the last example, we looked at convection plus radiation. That might be appropriate for maybe air in a room. You could have radiation transferring through the air. It's not absorbed very well by the air, but could be absorbed by the surface of you or whatever object we're looking at radiation impacting on and emitting from. In combination with convection for the air in the room, you can't have conduction, convection, and radiation, and that's because conduction and convection are simultaneously modeling both the same kind of phenomenon. So convection is just conduction plus fluid motion. So when you have convection, you can't also have conduction through that same medium. You're already accounting for the conduction with the convection heat transfer coefficient. Okay, so an opaque solid, a solid that radiation doesn't transfer through, you would have just conduction. If you have radiation able to transfer, like in a gas or a liquid where the radiation is at an energy that isn't absorbed very well by the liquid, then you could have convection plus radiation. If there's some sort of physical structure that stops the fluid from moving around very much, you might have radiation plus conduction in that too. If you have no physical medium inside, then you don't have conduction or convection, but you could still have radiation through it, and that's the case of a vacuum. All right, on to lecture 13. So this is the other half of what's on this particular tutorial test. We've got chapter 17's first half, 17, 1 through 3, and this is steady heat conduction. Steady heat conduction in plane walls. So at any point in the wall, Fourier's law of heat conduction says that the rate of heat flow is equal to thermal conductivity multiplied by cross-sectional area times the temperature gradient. And that example that we did earlier, where we found out that if the rate of heat flow is a constant, like in steady state, and the area and thermal conductivity are constants with position as well, then the temperature gradient must also be a constant, and therefore we get a linear temperature distribution. And that's what's proved in this example right here. So the rate of heat flow through a wall must be K times A, so thermal conductivity times the cross-sectional area times the temperature difference across the wall divided by the thickness of the wall, L, the length that we're conducting through. This is kind of similar to electrical conduction, so electrical flow. The current is equal to the conductivity times the cross-sectional area divided by the length of the resistor times the voltage difference that's placed across it. And so with that in mind, we're going to define thermal resistance as the driver of temperature flow, which is the temperature difference, driver of heat flow, I should say, the temperature difference, divided by the rate of heat flow, the heat current. Again, analogous to circuits, where R is defined as the voltage difference, the potential difference divided by current. So we have the resistance for a wall section with this definition ends up being L divided by thermal conductivity times the cross-sectional area. Again, analogous to the one for electrical resistance, where now we use electrical conductivity there. And for convection, I mean, why stop at conduction? We can just say, hey, what's the effective resistance for convection if we use the temperature difference now as the surface versus the free stream? Then convection resistance would end up being 1 over convection coefficient times surface area. And same thing for radiation. If we use that construction where we used the difference of squares twice to write an effective radiative heat transfer coefficient, then we have an effective radiative resistance as 1 over hrad surface area, and hrad substituting in emissivity, Stefan-Boltzmann constant, and these factors of temperature. Okay, so now we've got effective resistance for all three mechanisms of heat transfer. Now, once you've got these resistances, you can use this information to figure out what the temperature profile or temperature distribution, or maybe the total rate of heat flow would be if you know the extreme temperatures for some section like this in order to design insulating systems. So imagine we've got two walls in series and an air temperature over here and an air temperature over here. So maybe this is like the inside of an oven, and then outside the oven over here, and we've got two walls in between. Or maybe this is the inside of your house and this is outside in the winter, or maybe outside the house in the summer and inside the house in the summer. And we want to figure out what the rate of heat loss is. Then we can set up a system like this, where we have the temperature over here and the temperature of the wall being one thermal resistance, telling you the heat flow, where now we have a convection resistance out there. Then you've got a wall resistance for this temperature difference, and then another wall resistance for the temperature difference across it, and another convection resistance for the temperature from that wall to the free stream inside. And what makes this useful is the idea that in steady state, the rate of heat flow has to be a constant all the way across. So from the same logic that we use to generate the Kirchhoff's laws for electrical circuits, we could generate the Kirchhoff's laws for thermal circuits. You know that the heat flow is the same through all the different sections, and this allows you to say that by the heat flow being equal, you can compare one section to the next, to the next, to the next, and end up with the total heat flow has to equal the total temperature difference, the temperature from one fluid to the other fluid, divided by the sum of the different resistances. So for thermal systems as well as electrical systems, if you have resistors in series like this, then you add them up to find the effective total resistance. And this is quite convenient for figuring out the heat flow at the start, and then going through to find out what all the different temperatures are internally if you need to do that. Next up, thermal contact resistance. Whenever two real solids are in contact, like in this last example, you probably don't have a perfect connection from one surface to the next. You probably have some imperfect connection because the solids are rough at the microscopic scale. So unless you do some thermal compression bonding or something like that to make really perfect connection between the surfaces, then you have voids in the contact. And that means that the heat isn't going to be able to flow just across uniformly like we imagined in the last example, but you have some extra heat drop, extra temperature drop across the interface from this extra effective resistance to heat flow. And this is modeled by a thermal contact resistance. Now, thermal contact resistance by convention does not consider the area. So this is not a resistance in the same sense as the thermal resistance as we had here. It's a bit of a misnomer. You would have to also divide this number by whatever the area of the interface is to find out the real real resistance of that interface. So here's some contact conductances, HCs, which are the inverse of thermal contact resistance. Again, not the real resistance of the contact layer. And you see that for air, it ends up being maybe 3600, and this can be quite significant for different interface layers. So definitely will there's some examples in the practice problems where you'll get to explore this and see how this compares to different conduction resistances through solids, often important to consider and then minimize by using something like a thermal grease to fill this in. So even though the grease has a lower K value, so a lower thermal conductivity than the solid itself, it might be a good idea if it eliminates these air gaps so that you then don't have a thermal contact resistance. So the final topic is generalized thermal resistance networks. This is looking at how do we deal with if you've got these two surfaces that are in parallel here, and there's another surface here which is sort of in series with both of these in parallel. Well, the picture gives you an idea of how you might deal with this, and this is making a way that we can find out what the temperature difference should be across this whole thing, or find the total heat flow, or find the temperature at one point versus another point. But there's an implicit assumption in this, and this is really assuming that all of the heat that flows through that the heat flow in this object is kind of uniform from one section versus another. If it's much easier to flow through this K1 than it is to flow through K2, then really what you'd find is that the streamlines wouldn't just be in the conduction direction, they would sort of spill out into K2 towards the end, so you can have more in here and it'll generally equalize a bit more as you go into K3. Think about this picture here to get an idea for how that would work. If you have one section that's easier to flow through, then they would condense on the way towards it and then spill out after that. But to do this assumption is to assume that heat can flow perfectly in the perpendicular direction to the heat flow, so that these cross sections are sort of isothermal, and that's not really perfect. Another approximation you could do is to assume that heat doesn't flow in those directions at all, and that means you'd need to slice through this and say that all the heat that flows through here, flows through here, flows through here, flows through here, flows through here. So anything that's flowing through the brick has to have come from this plaster section, not from any of the plaster sections above, even if the plaster is a much worse conductor than the brick. So in reality, neither of these approximations are all that perfect. But what is true is that the real heat conduction with this bending of heat flow lines would be somewhere between these two assumptions, somewhere between assuming that heat can flow instantly in the perpendicular direction and that heat doesn't flow at all in the perpendicular direction. And that means that if you calculate it both ways, you can rest assured that the real heat flow would be somewhere between the two calculations.